Addressing modes is basically the way the operands are chosen during program execution. It is dependent upon the addressing modes of the instruction. Now, how the operands are chosen and how the computer system can access those operands is based on the addressing modes. It basically tells us how to treat the operand bits, and program use variable, because program use variable instead of direct constants. So we take data from the users most of the time, and variables are saved in memory or registers. Now, number of bits in instruction can reduce. Number of bits in the instructions can be reduced with the help of addressing modes. For example, if you have 1 million memory locations in memory, so the addressing size will be 20 bits of data, and if 20 bits of data if you want to retrieve. Operand size will be 20 bits, and so the instruction size will increase. So computer use addressing modes technique for the purpose of accommodating one of the following: to give programming versatility to the user by providing such facilities as pointers to memory, counters for for loop indexing of data and program allocation, and to reduce the number of bits in the addressing field of the instruction. Okay, now coming back to the addressing modes, the types. The first one is the implied addressing mode. In the implied addressing mode, operands are specified implicitly in the definition of the instruction. So the operands on which the data has to be performed, they are implicitly given into the instruction. For zero stack, this is basically used for the zero stack organization and single accumulator. For example, if we have an instruction, increment A, and in accumulator, we have to increment 1. So in this, it is already given that we have to increment the accumulator register. It is very explicitly given. So source and destination are both hinted into instruction. That means that where you get the data and where you have to store it are both given in the instruction itself. You don't have to decode the instruction to get the address and it will be somewhere else. So it is implicitly given in the instruction. And instruction is telling which data we have to work on, and we don't have to mention any other variable, value, or memory location. That is for the implied mode. Now, in the immediate addressing mode, operand is directly provided as constant. So no computation is required for collecting effective address. So for example, if we have this add operation in the first register, we have to store in the first register, there is, like we have to increment CZ. That means that in R1 plus 3. So our constant integer A is equals to 10. They are both examples of the immediate addressing modes. Now, operand range depends upon the address field length. If it is more than instruction length, will have to increase. Okay. In immediate mode, the data is given in operand. Data jo hai, it is given in the operands, and constants are used in immediate mode generally. Hashtag denote immediate mode. Mostly hashtags are used to denote the immediate mode. Mostly what happens is that when constants, for example, constant integer, if you are going to give the constant, like the constants are those basically variables whose value do not change during the execution of a program. So if you want such value to be executed, you use immediate mode over there. Register mode. In register mode, what happened is the operand is present in register number is written in instruction. So this is how where you have to fetch the instruction, you have to decode it, and when in case of executing it, you have to basically go into another register to fetch the operand. Instruction size will be small as register is less in general. 4 bits for 16 registers, so very fast. And speed in register mode, basically speed is an advantage because registers are really very smart, very fast. And in instruction decode, you have to opcode an operation value represent register number. So when you decode the instruction, opcode and operand value will be in the register, and you have to go to that register to fetch that operand. On that register, the data will be. So if you have 16 registers in memory, you use 4 bits of data. An effective address will be calculated as you go to the R1 and then fetch the data from it. So the effective address of the data will be where the address of the register will take you. Now, register indirect mode. Now, register indirect mode contains the address of the operand in memory rather than the operand itself. So what happens in this is that when you decode instruction, opcode and address of the operand will be telling what type of data you have to work on. Now the number of the register will be given when instruction will be first decoded. So when you go to in the first decoded, that means what this means is when you load the first register, and in accumulator you store the um, you store the value that is found at the R1 register. You go into the memory location where the R1 is stored, and then you get the data from there, and that is basically the data you're going to work on in the instruction. So when we go to register R1, we go to R1, for example, let's say we get 100, right? That is the memory location. So we go to the 100th memory location, and where the data is, for example, if your data is 200, right? So first, when we decode instruction, we go to the R1 register. In R1, we get a memory location that would say 100, and on the 100th memory location will be your data. So in the register indirect mode, it gives you you have to decode the instruction. Computer system have to decode the instruction basically like that. In this way, basically what happens is that the size of the instruction is reduced. So when the size of the instruction is used, basically the data bus is reduced and the system is cost effective. But memory size is more, register size is less, instruction size will reduce in this. Now, auto increment and decrement addressing mode. It is basically a special case of register indirect mode. And what has happened is that it is used for referencing same address again and again. It is time consuming. For example, if you have to access data in a constant mode, like for example, we get addresses after decode, and on that address we get the data of the operand, right? Now computations increase. Basically what happens is that in the indirect mode, because we have to decode the instruction, we have again and again, we have to go to the first, we get the R1, and then on that memory location, we get when we get to the R1, we get the memory location on which the data is. So the computations basically increase in this sense. So is in and auto in same happens with the auto increment and decrement mode as well. Some of the hardwares, there are some hardwares which support this kind of mode, and it basically works when we have an array of data and we have to access the data continuously, like when you have to access data in a continuous manner, like the index 0, then you have to access index 1 and 2 and etc. So we can't give, we can't have the instruction again and again, decoding. There will be a lot of computations if we have to decode the instruction again and again, go to the and like it is just another increment in the memory. Like for example, if a value is stored at index 0 and then the other value is stored at index 1, we don't have to run the whole instruction again. We don't have to decode whole the instruction again just to get to another index. So this auto increment and decrement mode helps in such situations, so in fetching the data sequentially. Now direct absolute or absolute addressing mode. In this one, the actual address is given in the instruction, and basically it is used to access variable. For example, if we have an instruction add of x, so in accumulator, we're going to just add x. It doesn't require any memory, it doesn't require computations. And because most of the programming languages, they use global and other variables, which are whose values are known at the execution time, so variables stored in the memory location. So if instruction size is fixed, it will not accommodate more. And effective address of this is where the operand is present. Effective address is at the instruction itself. So basically, effective address is at the instruction itself. We have a 16, let's consider we have a 16-bit instructions, and we have 4 for opcode. Address should be 12 bits, so it can't be more than that. Now in indirect addressing mode, it's very important. Indirect addressing mode is used to implement pointers in passing parameters. It requires the two memory access. Two memory access is required. But what do I mean by two memory access? Is that how we saw in the indirect mode is that like register indirect mode, we have to go to a register and then on that we find a memory location on that. But here that thing is doubled. Effective address will be the register indirect, will be like like register indirect mode. It will be on the like you will but basically it just implements memory instead of the registers. And on that we have you have to go to a memory location, and on that memory location you will find the address of another memory location. On that memory location we will find the value of the x, so that you can add into the accumulator. and the effective address would be basically, this is the effective address, the memory location, and its value on the X. Now, relative addressing mode. One more thing to add is that indirect and direct addressing modes, they are supported by basically most of the instruction sets and hardwares. They support direct and indirect addressing modes. Now, relative addressing mode, it is basically used for like operations like branch operations, basically jump operations, where the sequential when a program is sequentially running and there is a branch commit and it gets to another part of the program to be executed. So the effective address in that sense would be the program counter plus offset, and offset is the value of the branch. For example, if a program is running from a memory location, let's say 500 to 550, and then there are and like a branch comes, a program is running, sorry, at a location 500, right? And at the 500 location a branch comes and it asks the program execution to jump from 500 to 550. So there is a branch of how many 50 jumps is a branch of, right? Now the data has to be fresh. Now what happens most of the time is that the instruction size will reduce. Okay, so in that scenario, when you have to jump, the size of the instruction increases. So in that because of the offset, so however you will calculate where the data is supposed to be, you will calculate program counter, the current address plus the offset. For example, PC would be 500, and how much jump we have to do, 50. So the effective address would be 550 of that operand which we have to get the data of. Base register addressing mode. Now in base register addressing mode, it is used in the program relocation. Now consider a program in 100 memory location. Okay, now what happens is basically in the earlier we saw that effective address would be calculated on the basis of base plus that offset address. Now in this base register addressing mode, what we consider is that, because sometimes what happened is that when you're executing a program, right, and when it goes out into the branch, right, it goes back, like for example it takes there are certain IO operation that it has to wait for, or many number of reasons that it has to go into the temporary memory, and then it comes back into the main memory, and it is a known fact that it is not supposed to be loaded into the same location it was earlier. So most of the time what happens, if for example, if in a program location we are given like branch 500 or branch 50, branch 550, branch to 550, if an instruction is given, and if that program is again reloaded in the 400 location, now when it will go to the instruction that says branch 550, it will consider that instruction invalid. So in that scenario, the base register addressing mode is used, and what it says is that rather than giving the absolute address, we give the displacement only. Displacement means that how many codes or how many levels or lines of instruction we have to skip, and on which particular instruction we have to go. For example, if a program is running at 500 instruction, and it says to skip to 550, right? So the effective address will be calculated base register value plus displacement. Now 500 would be the base value, right? And how much displacement would be 550, right? So basically we need to see only displacement. So it doesn't matter if we write 550, it just matters that, okay, fine, we know the value of the base register, right? So if it is loaded in any memory location, if it will jump 50, or it will jump that many displacement branch that is instructions, it will come to the required operand to be performed operation on. Now, index addressing mode. It is used to access or implement array efficiently. Multiple registers required to implement, and any element can be accessed without changing instruction. One register will be dedicated to the index register. Whenever element is to be accessed, the effective address will be calculated as base address plus index register value. And here address field is not changed during instruction, only base address is fixed, and every element will be accessed via index register. Now, basically in arrays, what happened is that because the data is stored sequentially, right? So base address of an array given in address path instruction, you have to access element array index method is used. Basically, if you have to access the array elements, index addressing mode is basically a mode defined if you want to access your data sequentially, like it is stored and indexes in an array. So this mode is used, and multiple registers, it will become one index register. Now, that was all about the addressing modes. let's discuss about the famous architectures of RISC and CISC. There's CISC is the complex instruction set computer, and RISC is the reduced instruction set computer. In complex instruction set computers, CISC, the number of instructions are more, and because the number of instructions are more, the micro operations are less. And in RISC architectures, the number of instructions are less, but the micro operations are more. And the length of the instruction format is variable because instructions can be, like there is a large set of instructions, so all instructions cannot be of a fixed length. And in RISC, the instruction length has a fixed size because the instructions number of instructions are less, but micro operations are more. Now it has a large number of addressing modes. CISC has a large number of addressing modes, and in RISC there are few number of addressing modes, maximum to 4. And in the CISC computers, the cost is high, and RISC, the cost is low. CISC computers are more powerful, RISC computers are less powerful. RISC architecture systems are more less powerful. And there are several cycle instructions, and in RISC we have single cycle instruction. And in CISC computers, it manipulates directly with the main memory of the computer, and RISC computers, they manipulate in the registers. And they are microprogram control unit, and they are hardwired control unit. And the examples of CISC architecture include mainframes, Intel x86, Motorola 6800, etc. And the RISC architecture examples includes the MIPS, ARM, Spark, and Fugaku. Fugaku is basically a supercomputer in 2020. So that's about it for the presentation. Thank you so much for listening.